Hello everyone, welcome to another pre-calculus video. Today we'll be looking at limits and how to tell if they exist. The easiest way I can think of explaining a limit to you is to think about driving a car. When you are driving a car, your car has to speed up, right? Since we don't want everyone crashing into each other, we have speed limits. That means we speed up our cars up to, let's say, around 40 miles per hour, so our car is traveling faster and faster until it reaches 40 miles per hour. We don't want to get into any accidents or get any speeding tickets, so we don't go faster than 40 miles per hour. So with that in mind, let's look at our first problem here. We have to determine each limit and the value based on the piecewise function below. So first up, a limit exists if the left side of the limit equals the right side of the limit. When you look at these problems, they normally have a number, and if there's a minus sign, that means we got to read the graph from the left. If there's a plus sign, that means we have to read the graph from the right. So starting with A, we have the limit as x approaches -2 from the left. We have to figure out what that limit would be. So at x equals -2, we can see that from the left side of the graph, there actually aren't any y values, which means the function doesn't exist before x equals -2. So that means that this left side limit would not exist. So you can write DNE for does not exist. If we look at this graph from the right side, we can see that these y values are actually getting bigger and bigger, and it looks like they're approaching y equals 3. So the limit as x approaches -2 from the right would be 3. Now, in order for the limit to exist, both the left and the right have to equal each other. But since on the left side of -2 the limit doesn't exist, the overall limit wouldn't exist. So we would write DNE does not exist. So the last thing we have to do is evaluate this function at -2. Well, you can see that there's a solid point here at y equals 3, so f of -2 would be 3. The next x value we're looking at is 0. So let's look at it from the left side. We can see that as we approach x equals 0 from the left, these y values are getting smaller and smaller, and they're approaching y equals 0. So this limit would be 0. On the right side, it looks like these y values are getting smaller and smaller, and again they're approaching 0. So since the left side is 0 and the right side is 0, we can say that the overall limit is also going to be 0. So that limit exists. Finally, we have to evaluate the function at 0. So f of 0, looks like we have a solid point up here at y equals 4. So f of 0 equals 4. The next x value we have is x equals 2. So from the left side, if we're approaching x equals 2 from the left side, it looks like these y values are getting bigger and bigger, and they approach y equals 3. From the right side, it looks like all of these y values are staying the same, and it looks like it's approaching y equals 1. So the left limit would be 3, and the right limit would be 1. So since these two limits do not equal each other, the overall limit does not exist. Finally, evaluate the function at x equals 2, and the solid point is at y equals 1. So f of 2 equals 1. The next x value is x equals 5. So when we look at x from the left, all the y values are 1. When we look at it from the right, the y values are also 1. So the left limit is 1, the right limit is 1, which means the overall limit is also 1. Next, we have to evaluate the function at x equals 5. And since there's a hole here and we don't see any other points here at x equals 5, we can say that this function does not exist at x equals 5. The last limit we have is at x equals 7. So from the left side, it looks like the values are all 1. From the right side, there aren't any y values on this side of the graph, so this right side limit does not exist. So since the left side and the right side limits aren't equal to each other, the overall limit does not exist. Finally, evaluate the function at x equals 7. Well, the solid point here is at y equals 1, so f of 7 equals 1. Okay, so these next two problems are pretty much the same. We're looking at these graphs and looking at these x values. So the first one here is looking at x equals 3 from the left. Well, from the left, we can see that these y values are increasing and they're approaching y equals 5. From the right side, we can see that these y values are decreasing and they're approaching y equals 2. So the left side limit is 5, the right side limit is 2. That means that the overall limit does not exist because they aren't equal to each other. Can we evaluate f of 3? No, because there are no solid points at x equals 3. Next we have x equals 6. So from the left side, these y values are increasing and they're approaching 3. And from the right side, these y values are decreasing and also approaching 3. So the limit here would be 3 since they are equal to each other. Now the value at x equals 6 is 1 since the solid point is here at y equals 1. So for number 3, we have evaluate the function at x equals 1. So from the left side, you can see these y values are coming down and they're approaching y equals 2. From the right side, they're actually increasing and they're approaching 3. So the overall limit does not exist because these two aren't equal to each other. At x equals 1, the y value is 2. This is the solid point here. So next is x equals 7. So from the left side, these y values are increasing and increasing, and they're approaching y equals 4. From the right side, they're decreasing, and they're also approaching y equals 4. So the overall limit would be 4. What is the value at x equals 7? Well, that does not exist. As you can see, there's a hole right here. So for this next one, we're locating where each type of discontinuity occurs in the graph below. So a jump discontinuity, this happens at x equals -3. So if we're drawing this graph, we'd have to put our pen on the paper and then we'd have to jump all the way up here to continue drawing this graph. So that happens at x equals -3. The infinite discontinuity happens at x equals 2. As you can see, these x values, they really want to approach this x equals 2 line, but they actually never will. So this line is actually called an asymptote. Same thing on the right side, the x values really want to equal x equals 2, but they're never actually going to equal x equals 2. Meanwhile, the y values are going to go off into negative infinity and positive infinity. But we're never actually going to have a y value at x equals 2. And then finally we have a removable discontinuity. So this happens at x equals 4. Basically, if we're drawing a line here, we're going to have to stop here because there's a hole and then keep drawing the line. So that's the removable discontinuity. Okay, so now we're getting into these problems that actually require some math. This looks really complicated, so just remember to keep a cool head. I'm going to tell you step by step what we have to do. So the directions say, for each piecewise function below, solve for the missing constants so that the function is always continuous. You may use the provided grid to assist you. So what does it mean for a function to be continuous? Well, it means we can draw the graph and we never have to pick up our pen. So that means that at x equals -6, the y values have to be the same. So for when it says find a, we see a here in the second function, we basically have to make sure that the y value here equals the y value for this function at x equals -6. So the first step is we have to set this function equal to this function. So let's set it up. We have a third x plus 7 equals -2x plus a. So now we want to group our like terms, so we can add 2x over to this side. So we'll have 7/3 x plus 7 equals a. Now that everything is simplified, we can plug in our x value of -6. So 7/3 times -6 plus 7 equals a. If we evaluate this, this comes out to -14, and -14 plus 7 equals negative 7. So if this a value equals negative 7, then these two y's will be the same and the function will be continuous. Okay, the next constant we have is b, and our two functions are negative 2x plus a and bx minus 10. So we're also looking at the x value of 1. So let's set these two functions equal to each other. We have negative 2x plus a equals b times x minus 10. So we have negative 2 times 1. When we plug in the x value, we have negative 2 times 1 plus a equals b times 1 minus 10. If we add the 10 over to this side, we have 8 plus a equals b. Since we already solved for a up here, negative 7, we plug in negative 7 here, and we get that b equals 1. For this function, when a equals negative 7 and b equals 1, there will never be a hole on this graph, and that means the function will be continuous. Finally, we have this set of equations, and we're evaluating at x equals 4. So the first step, we have to set these functions equal to each other. Since we're dividing by 5 on both sides, we can just get rid of that, and we can simplify it down to x squared minus k squared times x equals 7x minus 3x squared. So next, let's plug in our x value of 4. We have 4 squared minus k squared times 4 equals 7 times 4 minus 3 times 4 squared. So you go ahead and do the math. We have 16 minus 4k squared equals 28 minus 3 times 16. You simplify as much as you can. You eventually get down to 36 equals 4k squared. Divide by 4, we get k squared equals 9. And then to get rid of this squared, we can do the square root of 9. And so k will equal the square root of 9. And k will equal positive or negative 3. Alright, finally we have problem number 7. We're given three functions here. We have f of x, we have g of x, and we have h of x. So it says evaluate and or simplify the expressions below. So we have f of x is 2x minus 1, and we're evaluating at f of 8. So we plug in 8 into this formula. We get 2 times 8 minus 1. That's 16 minus 1, and that equals 15. For h of negative 4, we're looking at this formula, and we're plugging in negative 4 for the x value. So we get negative 4 squared plus 1. That equals 16 plus 1, and that equals 17. So now we have this weird formula here, f of g of h of 2. So this looks confusing, but let's take it one step at a time. So as you can see, we kind of have to work backwards for this. Our first step is we have to find h of 2. So I've written down h of 2 is going to equal, we plug in 2 for this x squared plus 1. So we get 4 plus 1. So our h of 2 equals 5. So if we evaluate g at h of 2, which we found is 5, g of 5, we now take 5 and plug it into the g of x function, and we get 3 times 5, and that equals 15. So now we know that g of h of 2 is 15. So if we evaluate f of g of h of 2, we have f of 15, and we just plug in 15 into this function. So 2 times 15 minus 1 equals 30 minus 1, and that equals 29. Now we have g of g of g of 1. So the first step is to solve for g of 1. So we plug in 1 into the g function. We have 3 times 1 equals 3. So now we got to find g of 1. So g of 1, we know that g of 1 equals 3. So now we plug in 3 into the g of x function again. So we have 3 times 3 equals 9. And so finally we have to take g of g of 1, which we just solved is 9. So now we plug in 9 into the function, and we have 3 times 9 equals 27. So next we have g of f of negative 2. So our first step is to solve for f of negative 2. Remember that our f of x function is 2x minus 1, so we're plugging in negative 2 for x. We have f of negative 2 equals 2 times negative 2 minus 1, which is negative 4 minus 1. So f of negative 2 equals negative 5. So if we take g of f of negative 2, which is g of negative 5, we get 3 times negative 5, and that equals negative 15. And again, we get that by plugging in negative 5 into this g of x function. Next we have f of negative x. So all we're doing here is we're plugging in negative x into the f of x function. So we're getting 2 times negative x minus 1. We can simplify that as negative 2x minus 1. Next we have f of g of x. So we know what g of x is. G of x equals 3x. So all we have to do is replace the x in this function with 3x. So we get that the f of g of x equals 2 times x, which is now 3x minus 1. Simplify this further, we get 6x minus 1. Now we have h of g of x. So if we look at h of x, that function is x squared plus 1, and g of x is 3x. So anywhere we see a x, we're plugging in with 3x. So 3x squared plus 1. Now remember that when we have an exponent on the outside, we have to square both of these terms. So we have 9x squared plus 1. Finally, we have h of negative x. So we're taking negative x and we're plugging it into our h of x function. So we take negative x squared plus 1. Well, any negative squared is always going to be a positive number, so we can simplify that to x squared plus 1. And this final question here says, comment on your answer to h of negative x. What do you notice? Well, if we put in a positive x here and we put in a negative x here, they're always going to equal each other. So any negative x will be positive, which means that h of x will always equal h of negative x, which means that this is an even function. Now you should know by now what an even function is. Alright, so that does it for this video. There was a lot in this video, so just take it slow. Go back to each example I did. Try it out for yourself. If you have any questions, please leave it in the comments, and make sure to like and subscribe, and I'll see you on the next one.